Imagine you have a very long rubber band made of letters like a string of beads. You only have a tiny robot that can remember a limited number of colors, also called states. When the robot walks along the rubber band, after it has seen more beads than colors, it must see a color it has already seen before, so it has to repeat a state. Because the robot's memory is limited, some part of the bead string will be visited twice. That repeated part can be stretched, or pumped, any number of times, and the robot will still think it is walking over a legal string. The pumping lemma tells us this must happen for every regular language, the ones that a robot with limited memory, a DFA, can recognize. It is necessary because without this repeating part property, the language could not be handled by a finite state machine. We need the lemma to prove that some languages are too complicated for such a robot, that is, they are not regular. There exists an integer p, the pumping length, such that every string s in the language L with the length of s greater than or equal to p can be split into three pieces s equals xyz satisfying three conditions. Condition 1, the length of y is greater than 0, the middle piece y is not empty, we have something to pump. Condition 2, the length of xy is less than or equal to p, the part xy is short enough that it lies within the first p symbols of s. Condition 3, for all I greater than or equal to 0, the string xy raised to the I power z is also in L. You can repeat y any number of times, including 0, and you still stay inside the language. In plain words, any long enough word can be broken so that a middle chunk can be duplicated or removed, and the new word will still belong to the language. Mathematically, there exists p such that for all strings s in L, if the length of s is at least p, then there exist x, y, and z such that s equals x, y, z, and the length of y is greater than 0, and the length of x, y is less than or equal to p, and for all I greater than or equal to 0, x, y raised to the I power z is in L. Think of a DFA as a tiny maze with a fixed number of rooms, states. When you walk through the maze reading a long word, each letter tells you which door to take next. If the word is longer than the number of rooms, the pigeonhole principle says you must enter some room twice. You cannot have a one-to-one mapping between letters and rooms forever. The path from the first entry to the second entry forms a loop. That loop corresponds to the substring y in the pumping lemma. Because you can go around the loop any number of times, or skip it entirely, and still end up in the same final room, the DFA will still accept the altered word. The proof simply formalizes this intuition. With p equals number of states, any word of length greater than or equal to p forces a repeated state, giving the required xyz decomposition. Explanation: here is a kid-friendly recipe you can follow. 1. Assume the language L is regular so a DFA exists. 2. Obtain the pumping length p from the lemma. You don't need to know the exact number, just that it exists. 3. Pick a specific word W in L that is at least p characters long. Choose W cleverly, usually something that makes the pumping property hard to satisfy. 4. Break W into XYZ in every possible way that respects the conditions y greater than 0 and xy less than or equal to p. You have to consider all such splits. 5. Pump the middle part. Try I equals 0, remove y, and I equals 2, duplicate y, compute the new strings xy0z and xy2z. 6. Check whether any of these new strings fall outside L. If you can show that, for every allowed split at least one pumped version is not in L, you have a contradiction. 7. Conclude that the original assumption that L is regular is false, so L is non-regular. Think of it like testing a toy train track. You claim the track can be looped any number of times and still lead to the station. You pick a long track, cut it into 3 pieces, and try adding or removing the middle loop. If the train ever ends up in the wrong station, the claim is busted. A superscript n be superscript n such that n is greater than or equal to 0. The language says the same number of a's followed by the same number of b's. Pick p from the pumping lemma and choose w equals a to the p b to the p. Any decomposition xyz must have y consisting only of a's, because the length of xy is less than or equal to p. Pumping y with I equals 0 gives fewer a's but the same b's. For example, a to the p minus the length of yb to the p, which no longer has equal numbers, it falls outside the language. Therefore, the language is not regular. A to the p such that p is prime, suppose it were regular, Take P as the pumping length and choose W equals A to the Q, where Q is a prime larger than P. There are infinitely many primes. In any XYZ split, Y contains only A's and the length of Y is greater than 0. Pumping with I equals 2 gives A to the Q plus the length of Y, which is composite because the length of Y is at least 1, so the new length is not prime. Thus the pump string is not in the language, a contradiction. Therefore the prime length language is not regular. These examples illustrate the stretch or shrink idea. When the language demands a strict relationship such as equal counts or primality, pumping destroys that relationship. Many beginners make these mistakes. Forgetting the for all splits rule, the lemma requires that every possible XYZ that meets the conditions must keep the word in the language after pumping. Showing one bad split is not enough. Choosing a word W that is too short. If the length of W is less than P, the lemma says nothing. Always pick W with length greater than or equal to P. Allowing Y to be empty, the condition the length of Y is greater than 0 is crucial. An empty Y would let you pump nothing, which tells you nothing about the language. Misusing the pumping length. Some think P is a fixed number you can compute. It is only guaranteed to exist. You never need its exact value, just that it exists. Assuming the converse, the lemma is a necessary condition for regularity, not sufficient. A language can satisfy the pumping property and still be non-regular, for example some cleverly constructed languages. So you cannot prove a language is regular by only checking the lemma. Ignoring the XY restriction. The length of XY is less than or equal to P. This keeps the pumped part near the start of the word. If you place Y later, the lemma does not apply. Keeping these points in mind will prevent you from tricking the lemma. The pumping lemma is like a one-way test. If a language fails the test, it is definitely not regular. But passing the test does not guarantee regularity. There are languages that are not regular yet still manage to satisfy the pumping conditions. They are called pumping lemma compatible non-regular languages. Therefore, the lemma cannot separate every non-regular language from regular ones. Also, the lemma cannot help with properties that are not about repeating substrings, such as languages that require a global condition like the number of A's is a perfect square. Such languages may fail the lemma, but the lemma gives no information about many others. In short, the lemma is a useful detective tool, but it does not have a universal magnifying glass. Some tricky languages slip through. Another limitation, it works only for regular finite-state languages. For richer families like context-free languages, a different pumping lemma is needed. Both lemmas talk about pumping parts of a word, but they apply to different families of languages. Regular language pumping lemma, one repeated block Y can be pumped. The decomposition is XYZ, with the restrictions the length of Y greater than 0 and the length of XY less than or equal to P. Only one block is duplicated, because a deterministic finite automaton has only a single line of memory. Context-free language pumping lemma, there are two blocks that can be pumped simultaneously. The decomposition is UVXYZ, where V and Y are the two pumpable pieces. They may be empty but not both. The conditions are: first, the length of VXY less than or equal to P, meaning the pumped region is limited. Second, the length of VY greater than 0, meaning at least one of V or Y is non-empty. Third, for all I greater than or equal to 0, UV to the IXY to the IZ is in L. Why the difference? A push-down automaton, the machine for context-free languages, has a stack, so it can remember a nested structure. Pumping two parts lets you keep the balance between, for example, opening and closing parentheses. In regular languages, there is no stack, so only one loop can be repeated. In practice, to prove a language is not context-free, you use the CFL pumping lemma. To prove it is not regular, you use the regular language version. The CFL version is weaker, harder to break, because it gives you more freedom to choose V and Y, reflecting the extra power of the stack. Both lemmas share the same spirit. A long enough word must contain a repeatable pattern because the recognizing machine has only finitely many configurations.